Hello all. So today we are talking about chapter 10 and looking at body weight and composition for health and sport. The human body is a remarkable machine. Energy balance reflects quite literally a balance between the dietary energy one consumes and the metabolic and thermal energy produced by the body throughout the day. In order to maintain a given body weight, energy input or the diet must balance energy output, metabolism. If there is a long-term imbalance between energy input and energy output, body weight will either increase or decrease. A surplus of only 50 calories per day adds up to 18,250 calories or over 5 pounds a year. Conversely, a deficit of 50 calories per day will result in a 5-pound weight loss over a year. The term body image refers to the mental image we have of our own physical appearance, and it can be influenced by a variety of factors, including how much we weigh and how that weight is distributed. Body weight appears to be a major concern of many Americans. In a survey of U.S. adults, Ballin and others report body image dissatisfaction rates of 13.4 to 31.8% and 9.0 to 28.4% for women and men, respectively, depending on how dissatisfaction was measured. Similar findings have been reported at the high school and even the elementary school level, primarily with female students, and some research has found that 85% of both male and female first-year college students desire to change their body weight. So obesity or globesity is a worldwide epidemic in Western and Westernizing countries and is associated with poverty in developing countries. From 1980 to 2013, NG and others reported increases in overweight and obesity of 27.5% and 47.1% for adults and children, respectively. Worldwide, an estimated 2.1 billion people are overweight or obese. According to the Centers for Disease Control and Prevention, the prevalence of overweight and obesity has increased at an alarming rate in the United States over the past 3 decades. Ogden and others report that 34.9% of adults and 17% of children in the U.S. were obese in 2011 and to 2012. In a separate report, Ogden and others note significant relationships among socioeconomic status, gender, and obesity, with higher obesity rates in poorer females with lower education rates and in non-Hispanic Blacks and Hispanic groups. According to data from the National Center for Health Statistics, the prevalence of overweight and obesity among U.S. adults aged 20 years and older increased from 54.9% in 1988 to 1994 to 69% in 2011 to 2012. In the same time period, the prevalence of obesity increased from 11.3 to 17.7%. in children 6 to 11 years of age, and from 2.5 to 20.5%, or 95% in children 12 to 19 years. Sturm and Hattori report the prevalence of extreme obesity, BMI greater than 50 kilograms per meter squared, in the United States increased tenfold from 2000 to 2010, with a decline in the rate of increase since 2005. Based on current time trends, Wang and Lim predict increases in the global prevalence of overweight and obese preschool-age children from 6.7% in 2010 to 7.8% in 2015 and 9.1% in 2020. This is an alarming trend since obesity is associated with other comorbidities, most notably diabetes mellitus. Children in this generation might be the first in history to experience a decreased lifespan due to the health problems associated with excess body weight. As we shall see, being overweight or obese may contribute to the development of numerous health problems. So what is the ideal body weight? Most individuals have a perception of an ideal body weight for standing height, age, and gender that is usually related to physical appearance. Most research efforts have attempted to find an ideal body weight for good health. Actuarial data collected by life insurance companies during the past century have compiled into normal or desirable ranges of body weight for a given height and age. These height weight charts, such as the Metropolitan Life height weight charts appearing in many physicians' offices, represent the ideal weights at which Americans can expect to live the longest. Enhanced physical appearance may also improve one's body image and self-esteem, factors important to psychological health. Although society may create a perception of an ideal body weight for appearance, this perceived ideal body weight may or may not be in accord with reality, optimal health, or physical performance. An enhanced physical appearance may also influence performance in certain sports that involve judging of aesthetic movements, such as gymnastics and diving. There appears to be no sound evidence to suggest a specific ideal weight for a given individual. Instead of ideal body weight for height, for health and performance, a more appropriate concept is healthy body weight, which is grounded in the concept of healthy body composition. Many factors will influence the body weight for a given individual, not the least of which is the measurement error in various body composition assessment techniques, a topic we talk about in this chapter. The major focus of this chapter is to discuss general guidelines that have been proposed for body composition and body weight relative to health and physical performance. Although height weight charts have been used to screen for normal body weight in the past, the Body Mass Index, or BMI, is the current standard, which is also based on height-weight relationship. The BMI is also known as quintile's index, is a weight-height ratio. Using the metric system, the formula is body weight in kilograms divided by height in meters squared. In English units, the formula is body weight in pounds times 705 and divided by height in inches squared. In general, a BMI range of 18.5 to 25 is considered to be normal for adults. Adult BMI categories for normal weight, overweight, obesity, and disease risk are presented in Table 10.1. We will discuss waist circumference, patterns of fat deposition, and risk of disease later in the chapter. Calculating the BMI for children and teens is somewhat more complex and includes both age and gender. The BMI is used as a screening tool to identify possible weight problems for children and both the Centers for Disease Control and Prevention and the American Academy of Pediatrics, or AAP, recommend the use of BMI in children beginning at 2 years old. The CDC has developed BMI for age growth charts for girls and boys that can be consulted to provide a percentile for a child's or teen's sex and age. The percentile ranking places the child in one of the following 5 categories: underweight, which would be less than the 5 percentile, healthy weight, 5 to less than 85 percentile, and overweight, 85 to less than 95 percentile, and obese would be greater than the 95 percentile. Severely obese is considered to be greater than 120% of the 95th percentile. Excess body weight may affect physical performance as well. For some athletes, simply being a little overweight may prove to be detrimental to physical performance because it costs energy to move the extra body mass. In contrast, increased body weight, provided it is of the right composition, may be advantageous to other athletes. At the other end of the body weight continuum, weight losses leading to excessive thinness also may have an impact upon health and physical performance. Anorexia nervosa and bulimia nervosa are 2 serious health disorders associated with obsessive concern with body weight. Hudson and colleagues estimate prevalence rates of 0.9% anorexia nervosa and 1.5% bulimia nervosa and 3.5% binge eating disorder in females. Although losing excess body weight may improve in performance in some sports, excessive weight losses may have a negative impact on both health and athletic performance. The preceding discussion is focused on extremes in body weight. It is important to stress that body weight is not synonymous with optimal body composition for health and performance. The major focus of this chapter is on the basic nature of body composition and its effect on health and physical performance. The following 2 chapters deal with weight control methods used to maintain or modify body composition. In general, a BMI range of 18.5 to 25 is considered to be normal for adults. Adult BMI categories for normal weight, overweight, obesity, and disease risk are presented in Table 10.1. We will discuss waist circumference, patterns of fat deposition, and risk of disease later in the chapter. So what are the values and limitations of the BMI in relation to determining whether an individual possesses normal body weight for a given height? The BMI may be a useful screening device for health problems. As we will discuss in later sections of the chapter, high BMI values may be associated with overweight or obesity and various metabolic diseases such as diabetes mellitus, cardiovascular disease, and metabolic syndrome. At the other end of the continuum, low BMI values may also be the result of hormonal imbalances, malnutrition, or eating disorders. Specific BMI values related to potential health statuses are presented later. BMI is also used in large epidemiological studies instead of more sophisticated body composition assessment techniques as an apparent indicator of increased prevalence of overweight or obesity in a population over time. Assuming the existence of standardized measurements of body weight and height, such studies can detect associations between apparent increases in body fatness, increased BMI, and health. The use of BMI as an indicator of fatness is based on the assumption that increased BMI over time is due to increased body weight, the numerator, which in most individuals is most likely the result of increased adiposity over time. Since the mid-1980s, the Centers for Disease Control and Prevention have been tracking the prevalence of obesity, operationally defined as BMI greater than 30, in the United States through the Behavioral Risk Factors Surveillance Survey. These data can be viewed at the following CDC website. Here you see there are some limitations of the body mass index, and although it's generally a good indicator of overweight and obesity, it does not assess body composition in any given individual. Two individuals may have the same height and weight, but one may have excess body fat while the other may be very muscular with a low body fat percentage. And although a BMI is not perfect and may be inappropriate for use with very muscular individuals, it is a good guide that the average person may use to think about a healthier body weight. However, other methods are needed to evaluate actual body composition. So calculating the BMI for children and teens is somewhat more complex and includes both age and gender. The BMI is used as a screening tool to identify possible weight problems for children, and both the Centers for Disease Control and Prevention, or the CDC, and the American Academy of Pediatrics recommend the use of BMI in children beginning at 2 years old. The CDC has developed BMI for age growth charts for girls and boys that can be consulted to provide a percentile for a child's or teen's sex and age. The percentile ranking places the child in the categories we discussed earlier. What is the composition of the body? The human body contains many of the elements of the earth, 25 of which appear to be essential for normal physiological functioning. Most of the human body, about 96%, consists of 4 elements: carbon, hydrogen, oxygen, and nitrogen, and various combinations. These 4 elements are the structural basis for body protein, carbohydrate, fat, and water. The remaining 4% of the body is composed of minerals, primarily calcium and phosphorus in the bones, other minerals such as chlorine, sulfur, sodium, and magnesium, and the micro minerals iron, cobalt, zinc, iodine, selenium, fluorine, manganese, molybdenum, chromium, and others that were discussed in Chapter 8. Because body composition may have a significant impact on health and physical performance, scientists have developed a variety of techniques to measure various body components. Wang and others noted that depending on the purpose, body composition may be evaluated at 5 levels: the atomic, molecular, cellular, tissue system, and whole body levels. Of major interest to body composition scientists are 4 major body components: total body fat, fat-free mass, bone mineral, and body water. The location of body fat deposits, whether under the skin, which is subcutaneous, or deep in the body, which is visceral, is related to health status. As will be discussed later in the chapter, large deposits of visceral fat are associated with diabetes mellitus, cardiovascular disease, and metabolic syndrome. Each of these components has a different density. According to Archimedes' principle, density, also known as specific gravity, equals mass divided by volume. In body composition, density is usually expressed as grams per milliliter or grams per cubic centimeter. The standard for comparison is water, which has a density of essentially 1.0 or 1 gram per milliliter, the exact density depending on the water temperature. Corresponding densities for other components are approximately 1.3 to 1.4 for bone, 1.1 for fat-free protein tissue, and 0.9 for fat. The total body density value may be used to estimate the body fat percentage, with a higher density representing a greater amount of fat-free mass and a lower amount of body fat. The total human body density may range from approximately 1.010 grams of milliliters, estimated 40% fat, to 1.090 grams of milliliters, or 4% fat. Although there is little individual variance in the densities of fat and water, bone and fat-free densities may vary considerably between individuals and as a function of health status. As a result, the use of constant densities of these components is a source of error in attempts to estimate body fat percentage from total body density. Depending on the purpose, body composition is usually analyzed as 2, 3, or all 4 components. The 2 components most commonly measured are total body fat and fat-free mass. Bone mineral content and body water may be measured with more elaborate techniques. Wang and others also introduced a 6-component model, which, in addition to these 4 components, adds measurement of soft tissue, minerals, and glycogen. Total body fat in the body consists of both essential fat and storage fat. Essential fat is necessary for proper functioning of certain body structures such as the brain, nerve tissue, bone marrow, heart tissue, and cell membranes. Essential fat in adult males represents about 3% of the body weight. Adult females also have an additional 9 to 12% of essential fat associated with normal reproductive function. This additional sex-specific fat gives females a total of 12 to 15% essential fat, although this amount may vary considerably among individuals. Storage fat is simply a depot for excess energy, the quantity of which may vary considerably between and within individuals due to factors discussed later in the chapter. Some storage fat is found around body organs for protection, but about 70 to 80% of total body fat is found just under the skin and is known as subcutaneous fat. Cellulite is a certain type of subcutaneous fat, more common in females than males. According to Rossi and Katz, cellulites is caused by the sequestration of adipocytes in chambers surrounded by connective tissue. The peripheral adipocytes in these chambers expand with water, stretching and thickening the connective tissue, giving rise to a dimpled surface appearance perceived by many as aesthetically undesirable. Other storage fat is located deep in the body, particularly in the abdominal area. This deep fat is referred to as visceral fat, which is noted later as associated with increased health risk. Fat-free mass primarily consists of protein and water, with smaller amounts of minerals and glycogen. The tissue of skeletal muscles is the main component of fat-free mass, but the heart, liver, kidneys, and other organs are included also. A more common term, often used interchangeably with fat-free mass, is lean body mass. Technically, however, lean body mass includes essential fat. In the simplistic 2-component model of body composition assessment, total body mass is the sum of fat-free mass, or lean body mass, and fat mass. For example, a 200-pound sedentary person with an estimated 30% fat is assumed to have a fat mass of 60 pounds. And a corresponding 70% or 140 pounds of fat-free mass. Bone gives structure to the body, but it is also involved in a variety of metabolic processes. Bone consists of about 50% water and 50% solid matter, including protein or collagen and minerals. primarily calcium and phosphorus. Although total body weight, bone weight, including water and protein, may be 12 to 15% of the total body weight, the mineral content is only 3 to 4% of total body weight. As was discussed in Chapter 9, the average adult body weight is approximately 60% water. The remaining 40% consists of dry weight materials that exist in this internal water environment. Some tissues, like the blood, have a water content, whereas others, like adipose tissue, are relatively dry. The fat-free mass is about 70% water, while adipose fat tissue is less than 10%. Under normal conditions, the water concentration of a given tissue is regulated quite nicely relative to its needs. When we look at the percentage of the body weight that may be attributed to a given body tissue, the weight of that tissue includes its normal water content. So what techniques are available to measure body composition? How accurate are they? This is an interesting conversation. The measurement of body fat has become very popular in recent years. Many high school and university athletic departments routinely analyze the body composition of their athletes in an attempt to predict an optimal weight for competition. In some sports, such as wrestling, measurement of body composition is mandated by various state or national sport associations. Fitness and wellness centers also usually include a body fat analysis as one of their services. Unfortunately, some of the individuals who analyze body composition in these situations are unaware of the limitations of the tests they employ. The only direct, accurate method of analyzing body composition is by chemical extraction of all fat from body tissue, which is obviously not appropriate with living humans. Thus, a variety of indirect methods have been developed to assess body composition. Some are relatively simple, such as visual observation by an experienced judge, and others are rather complex, such as nuclear magnetic resonance imaging. Using multi-million-dollar machines, indirect methods are used to measure body fat, lean body mass, bone mineral content, and body water. Some techniques are also used to measure fat in specific locations of the body. Most field methods used, such as skin folds or bioelectrical impedance analysis, or BIA, are two-component models, as are some laboratory methods such as hydrostatic weighing and air displacement plethysmography. Going indicates that methods based on two-component models are associated with greater errors than are methods based on multi-component models, such as dual energy X-ray absorptiometry, or DEXA. 3 and 4 component models that combine measures of body density with body water and mineral content dramatically reduce the errors associated with the traditional simplistic 2-component model. So we'll be going over these techniques as we go through. All indirect assessment techniques discussed in this section that are employed in vivo, or in the living, breathing individual, even technologically sophisticated ones, ultimately provide only estimates of various components of body composition, including body fat. These estimates vary in precision and are prone to error depending on the technique. Such errors usually are expressed statistically or as standard errors of measurement or estimate, which can be used to show the accuracy of the body fat measurement. For example, a wrestler undergoes preseason body composition assessment. A skin fold technique predicts 7% body fat and has a standard error of measurement, or SEM, of 3%. If the same wrestler is measured repeatedly with no change in body composition, the technique will generate different estimates. Approximately 68% of these actual measurements will be within 1 SEM, or standard error of measurement, of the average value. So there is a 68% level of confidence that the actual body fat percentage of this wrestler is between 4 and 10%, plus or minus 1 SEM. This is actually an example of a doubly indirect technique, since an estimate of body density is used to estimate body fat percentage. Body composition assessment should only be considered as providing a range, which may include the actual body fat percentage at a certain level of confidence, not as a precise measurement. A number of body composition measurement techniques are highlighted in Table 10.2, but only the more commonly used or promising techniques will be discussed. The selected body composition technique will depend on the availability of resources. the laboratory versus field-based nature of assessment, and other factors. Regardless of the chosen method, the following general guidelines should be followed. The measurement error will be smaller if the same method is used to assess changes in an individual throughout the period of assessment. The skin fold measurements may have a lower inter-measurer reliability due to differences in grasping technique and anatomical site location. Measurements should be taken by the same trained technician throughout the assessment period. Population-specific equations have been developed from homogeneous subjects based on characteristics such as gender, age, ethnicity, and athletic group. The individual being assessed should belong to the population upon which the equation was developed. Hayward and Wagner's book provides prediction formulas for various athletic populations. One of the most common research techniques for determining body density is hydrostatic weighing, also known as underwater weighing or hydrodensitometry. Hydrostatic weighing is a volumetric technique based on Archimedes' principle that a body immersed in a fluid is acted upon by a buoyancy force that is directly related to the volume of water displaced. Because fat is less dense and bone and muscle tissue are more dense than water, a given weight of fat will displace a larger volume of water and exhibit a greater buoyant effect than the corresponding weight of bone and muscle tissue. Different formulas are recommended for determination of body density depending upon the weight, age, and sex of the individual. Although this technique was once referred to as the gold standard in body composition analysis, it is an indirect two-component model with associated weaknesses. As previously mentioned, the assumption that the density of the fat-free protein tissue is 1.1 gram per milliliter may not be valid for all individuals, such as athletes and older persons. The standard error is still about 2 to 2.5%. Thus, Wagner and Hayward note that the underwater weighing should not be regarded as the gold standard because of these errors. The hydrostatic weighing technique is rather time-consuming and difficult for some individuals. For example, the quality of the data is affected by the subject's comfort level with the water medium, so non-swimmers may have difficulty with the technique. Other techniques, such as air displacement plethysmography, have been developed for either research purposes or practical applications. So, as we were saying, the air displacement plethysmography, or ADP, is a volumetric technique, sometimes referred to as body plethysmography. Subjects enter a dual-chamber plethysmograph designed to measure the amount of air they displace. It's also called the BOD pod, somewhat comparable to the water displacement technique of underwater weighing. It is portable, easy to operate, requires little time, and eliminates the necessity of going underwater. Several clear advantages compared to underwater weighing. Several reviews, including one of Wagner and Hayward, have noted that it may be more valid and more reliable than hydrodensitometry for certain individuals, such as those who fear underwater submersion, but has similar limitations. Overall, Noreen and Lemon indicate that ADP appears to be a reliable method to use in tracking changes in body composition in individuals over time. Skin folds are designed to measure the thickness of subcutaneous fat in millimeters at specific anatomical sites. It appears to be the most common procedure for non-research purposes. The skin fold thickness values are inserted into an appropriate equation to estimate total body density, which in turn is used in another equation to estimate body fat percentage. Some formulas have also been developed for specific athletic groups. To improve the accuracy of this technique, skin fold measures should be obtained from a variety of body sites because using a single skin fold site may be unrepresentative of total storage fat. The test should also be administered with an acceptable pair of skin fold calipers by an experienced tester. Ultrasound techniques are also available to assess skin fold thicknesses, but these are more expensive than calipers. Orfanadou and others found that measurements of subcutaneous body fat with skin fold techniques were comparable to those obtained by ultrasound and computed tomography, suggesting that the use of skin fold calipers in the clinical setting is appropriate. Utter and Hager reported that the ultrasound provided similar estimates of fat-free mass as hydrostatic weighing in high school wrestlers and suggested it could be an alternative field-based method. 10.4 is a schematic drawing showing the skin fold of fat that is pinched up away from the underlying muscle tissue, and then B is the measurement of the tricep skin fold. Precise location, a vertical fold on the posterior aspect of the right arm, halfway between the acromial process of the shoulder and the olecranon process of the elbow is recommended in this particular case. Bioelectrical impedance analysis, or BIA, is a little more expensive than the skin fold calipers, but it is still a practical field technique. It is based on the principle of resistance to an electrical current that is applied to the body. The less the recorded resistance, the greater the water content, and hence the greater the body density. Early research with BIA revealed large standard errors in predicting lean body mass, so it was not considered to be very valid. However, Joffrin, in an update on BIA, reported that it had been compared with medical impedance meters and with dual X-ray absorptiometry measurements and found reasonably accurate, except for individuals with very low or high BMI. The BIA instrument may have pre-programmed prediction equations to use, which ideally should include age, gender, and ethnicity. Most do not have athlete-specific equations based on a multi-component model, including total body water, as noted in a review by Moon. In its position stand on nutrition for the athlete, the Academy of Nutrition and Dietetics, Dietitians of Canada, and American College of Sports Medicine indicated that the prediction accuracy of BIA is similar to that of skin fold assessment, but BIA may be preferable because it does not require the technical skill associated with skin fold measurements. Pitchard and others reported valid BIA equations for female runners, but recommended research to valid equations for other athletes. In this particular figure, you'll notice they're doing bioelectrical impedance analysis, which is a low voltage current optimally conducted through a body with a high fat-free mass or high water content, while high fat mass or low water content offers resistance to the current. Electrodes are placed at the hands and feet. Dual energy X-ray absorptiometry, or DEXA, or DXA, is a computerized X-ray technique used to image body tissues and has been used to assess bone mineral content, fat-free mass, and body fat concurrently. DEXA may also be used to assess regional fat depots, such as deep visceral fat, as can other sophisticated techniques such as magnetic resonance imaging, or MRI, and computed tomography, CT. DEXA is also used in clinical settings to detect the presence of osteoporosis. And this particular figure, dual energy X-ray absorptiometry, or DEXA, is a method that measures body fat by releasing small doses of radiation through the body that a detector then quantifies as fat, lean tissue, or bone. The scanner arm moves from head to toe, and in doing so can determine body fat as well as bone density. DEXA is currently considered the most accurate method for determining body fat, as long as the person is not too obese to fit on the table and or under the arm of the instrument. The radiation dose is minimal. Near-infrared interactance is another device that's marketed commercially based on near-infrared light interactance. In essence, infrared light passes through the tissues, and its interaction with tissue components is used to predict body fat. The FutureX Corporation's 6100 model is one example of such a device. Wagner and Hayward reported somewhat higher standard errors of measurement with the near-infrared interactance greater than 3.5% in separate studies comparing various body composition assessment techniques with a three-component model as the criterion method. Moon and colleagues concluded that near-infrared interactance was an acceptable field method for college-aged females, but not for college-aged males. Orthopometry, or measurement of body parts, is an inexpensive, practical method to assess body composition. Body measurements include circumferences using a tape measure, such as the neck and abdomen, and bone diameters, such as the hip, shoulders, elbow, and wrist. Although circumference or bone diameter measurements may be incorporated into various equations to predict body fat and lean body mass, Moon and colleagues reported high standard errors of measurement for various equations using abdominal and or neck circumferences generated for use on males in the United States Army, Navy, Air Force, and Marine personnel. Circumference measurements of the abdomen, hips, buttocks, thigh, and other body parts may indicate regional fat distribution. The pattern of fat distribution may be an important indicator of major health problems such as obesity, diabetes, and metabolic syndrome. The principal measure of regional fat distribution is the waist circumference. The abdominal or waist girth measured by flexible tape at the narrowest section of the waist as seen from the front. The waist circumference is a good screening technique for regional fat distribution, but it does not provide an accurate measure of deep visceral fat, such as provided by CT or MRI techniques. The multi-component model uses several methods such as densitometry, total body water, and DEXA to reduce the errors associated with any single method and to provide information on body fat, body water, bone mass, and lean body mass. Lohman and Going recommend use of a multi-component model when assessing body composition in children and youth, including waist circumference, selected skin folds, and DEXA. Wagner and Hayward note that this multi-component model is now regarded as the gold standard in body composition assessment and should be used when feasible. Lara and others recently reported that aggregate 2, 3, and 4-component models improve the accuracy of changes in fat mass in overweight and obese subjects compared to any single 2, 3, or 4-component approach. Shared variances between the 4-component aggregate models and the 3 and 2-component aggregate models were 0.99 and 0.72 respectively. So what problems may be associated with rigid adherence to body fat percentages in sport? Table 10.2 lists most of the methods used to estimate body composition. Historically, hydrostatic weighing has been the criterion method by which other techniques have been validated. More recently, DEXA or 4-component model has been used as the criterion. As has been previously discussed, different techniques have sources of error, which contribute to a different standard of errors of measurement and resulting differences in estimated body fat percentages. Compared to the 4-component model, DEXA and total body weight underestimated fat mass gain and overestimated fat-free mass gain in subjects gaining weight, while ADP underestimated fat mass gain and overestimated fat-free mass gain. The researchers attributed this bias to the erroneous assumption in 2-component models of a constant hydration stat for fat-free mass. Aspects of the NCAA weight policy requiring additional research attention include the effect of overhydration, use of skin fold calipers for different manufacturers, and use of the Brosick equation to estimate fat percentage from estimated body density, which may erroneously increase muscle weight in African American wrestlers. Given the problems with assumptions underlying the various methods of body composition determination, body fat percentage estimates are only approximations. The rigid use of body fat percentages in weight control sports such as gymnastics and wrestling may lead to excessive weight loss. For example, if a wrestler who has 8% fat is required by his coach to reach 5% fat, the wrestler may already be at 5% fat because the skin fold technique has a 3 to 4% standard error of measurement. Losing extra weight may be very difficult for the wrestler because he is already near minimal body fat levels. In his attempt to heed the coach's mandate, the wrestler may lose lean muscle mass, which will place him at a competitive disadvantage in young athletes. Such practices may also lead to disordered eating and possibly clinical eating disorders. So how much should I weigh or how much body fat should I have? It's a complex question, and that response depends on whether you are concerned primarily about appearance, health, or physical performance. From the perspective of physical appearance, you are the best judge of how you wish to look. However, a distorted image may lead to serious health problems or impairment in physical performance. For example, many individuals do not recognize that they are overweight and may suffer adverse health consequences. Already thin individuals who desire to be even thinner may be prone to eating disorders. Muscular bodybuilders who perceive themselves as not sufficiently muscular may suffer psychologically. In a survey of U.S. adults, Fallon and colleagues reported body dissatisfaction prevalence estimates of 13.4 to 31.8% for females and 9 to 28.4% for males, with evidence of a plateau or decline in dissatisfaction compared to previous estimates. The effect of body weight and body fat on physical performance is discussed in later section. Although some general guidelines are presented here, the effect of body weight and fat on health has received considerable research attention. Although being underweight may impair health, most of the focus has been on excess body weight and fat, particularly the relationship of obesity to health. By medical definition, obesity is simply an accumulation of fat in the adipose tissue. Obesity is also referred to as a disease or disorder and is the most common nutritional health problem in North America. The actual measurement and determination of clinical obesity is a controversial issue. Several approaches have been used to define the point at which a person is classified as clinically obese. Unfortunately, our present level of knowledge does not provide us with the ability to predict precisely what the optimal weight or percent body fat should be for health in any given individual. However, some general guidelines have been developed by various professional and health organizations. Body fat percentage categories from essential to very poor or overweight or obese for males and females by age are presented in Table 10.3. Several points should be kept in mind when using such tables. All body fat prediction methods contain a source of error. The essential, very lean, and excellent categories pertain to athletes competing in weight control sports or sports where excess body fat may be a disadvantage. As will be discussed later, obesity generally increases health risks, but some individuals with higher body fat percentages may not develop obesity-related health problems if they are otherwise physically fit and consume a healthful diet. Finally, as will also be discussed later in the chapter, the location of the fat in the body may have significant health consequences. Body mass index may be used as a crude technique to calculate a target body weight. According to guidelines from the National Academy of Sciences and the National Institutes of Health, a person with an ideal body weight will have a BMI of greater than 18.5 up to less than 24.9. The BMI equation can be rearranged to solve for a target weight as follows. Weight in kilograms is equal to desired body BMI, a value from 18.4 to 24.9 times height measured in meters or in inches squared, divided by 705 if you're looking at pounds. Higher BMI values are usually but not always associated with overweight and obesity as described in Table 10.1. BMI values are based on height and weight and should not be confused with body fat percentages. Most Americans are focused on weight maintenance or weight loss, strategies of which are covered in Chapter 11. At the other extreme, low BMI values may be indicative of starvation. The Food and Agricultural Organization has proposed the following BMI categories as indicative of use of a BMI less than 18.5 as criterion for chronic energy deficiency or CED. CED grades and associated BMI values are based on a physical activity level, which is looking at measured energy expenditure or intake divided by measured basal metabolic rate of less than 1.4. The POW concept is discussed in Chapter 3 and in 11. The health and performance of some Americans will actually benefit from weight gain consisting of fat-free mass, strategies of which are discussed in chapter 12. So essentially you're looking at increasing lean body mass. So if we look at the key concepts, body mass index does not measure body composition, but it may be useful as a screening device to determine whether one is overweight or obese. Overweight and obese are not synonymous terms. It is possible to be overweight but not obese, or at a normal weight with too much body fat. The body consists of 4 components: body fat, protein, minerals, and water. However, for practical purposes, body composition may be classified as consisting of 2 components: fat frame weight, which is about 70% water, and body fat. All techniques that are currently used to measure body composition, primarily body fat, are indirect and prone to error. Even the hydrostatic weighing technique, which was once considered to be the most accurate, may be in error by 2 to 2.5%. Our present level of knowledge does not provide us with the ability to predict precisely what the optimal body composition should be for health or physical performance. However, BMI and body fat levels higher than normal are associated with increased health risks.